Today we in our class will be discussing about the concept of statically indeterminate beams. What do we mean by statical indeterminacy? Though we are already familiar with the definition of statical indeterminacy, but let's try to see what do we, with the help of example, what do we mean by the statical indeterminacy of the beams. In order to make you understand, let's suppose we have a cantilever beam. We take a cantilever beam and let's suppose that this cantilever beam is subject to load. It is, we know a cantilever beam is fixed at one end, and this beam, the cantilever beam, which is, we know it's always fixed at one end. Let's suppose the span of the beam, that is the length of the beam, is, say for example, L. Okay, and if we do the analysis of this beam, of this cantilever beam, which is subject to load, sorry, if we start doing analysis of this cantilever beam, which is subjected to any sort of load, okay, and its cantilever beam is fixed at one end, we know that, and we call this end as end A, we call this end as end B, let's suppose, and we say the span of the beam is, say for example, L. Okay, we know as far as the fixed end of the beam is concerned, at the fixed end of the beam we have reaction, what we call as reaction at end A, reaction at end A, and at the fixed end we also have the moment, that is a fixed moment, that is what we call as MA, the reaction moment MA. The reaction moment MA and the reaction RA are in response to the load that acts on the cantilever beam at any point. Okay, let load P be acting on the cantilever beam. Then in response to the load P acting on the cantilever beam, we know at the fixed end we have reaction RA and we have a fixed moment that's equal to MA. If this load is acting at some distance from the fixed end, let's suppose it is acting at a distance, say for example at any distance, let's call that as L by 4, L by 3, whatever it is. And we have done till now, if we are asked to calculate the value of reaction, we simply write down the equations of equilibrium. We write Ra minus P is equal to 0. Therefore, as far as Ra is concerned, we get the value of Ra is equal to P. As far as the reaction is concerned, the value of the reaction is equal to the load applied. Since we are already knowing how much is the load, therefore we can calculate the value of reaction. Okay, so this is our equation 1. In the same way, if we are asked to calculate the value of this fixed moment we have anti-clockwise, we write this as MA, and this moment, because of load P, will be PL by 4, and this moment is trying to rotate the beam in clockwise direction. We write this as minus PL by 4, and this is equal to 0. Therefore, MA becomes equal to PL by 4. Now we have two equations. We have equation 1 and equation 2, and we have two unknowns. Our unknown is reaction, our unknown reactions, I mean to say, our unknown reactions are two. We have unknown reaction Ra, we have unknown moment Ma. Okay, so we have two unknowns and the number of equations that we have are 2. So when we have two unknowns, when we have two unknown reactions, we have two unknown reactions, and we have two equations to find the values of those two unknown reactions. Therefore, we say this is a case of statical determinacy. This is a case of statically determinate beam. Okay, this is statically determinate because our number of unknowns is equal to the number of equations. So this is a case of, let's say this is statically determinate case. This is statically determinate case. When we say this is statically determinate case, it simply means that the number of equations is equal to the number of unknowns. So we can simply say the number of equations is equal to the number of reactions we have. Therefore, this is a case of statically determinate case. Now let's replace this cantilever beam by a support. I mean to say, we do the same analysis. We have the same cantilever beam of span L. Okay, but apart from, let's say we give it an additional support. That is, let's take a cantilever beam. Let's suppose we have a cantilever beam like this. Okay, it's fixed at one end. The cantilever beam is fixed at one end. It's end A, this is end B, and the length of the beam or the span of the beam is, say, for example, L. Okay? The total length of the beam is, say, for example, L. Now again, the same beam is subjected to load B at one of its points, such that again we assume that let this distance be equal to L by 4. Let this distance be equal to L by 4. Okay. Now, again, like previous case, this question is same as the previous case, but let's do one more thing, that at its free end, let's give it a support. That is, let's say at end B we are supporting the cantilever beam. Okay, so we are giving it a support, and let's suppose the support is in the form of a, let's give it a roller support. Okay, so now this is a cantilever beam, and this cantilever beam is being supported at one end. Okay, now we'll be having two reactions. We'll be having reaction at end A, what we call as RA, and end B will also offer the reaction. We'll be having reaction at end B, that is RB, and we will be having, since this is a fixed support here, at end A there is fixed support, at end A there will be the moment, the fixed bending moment, what we call as MA. At end B, we will not be having the moment, because we have already seen, once we are drawing the shear force and bending moment diagram, at the roller support or at the pin support, there is no bending moment. It does not offer any reaction moment. Okay, we already know this. So now the number of unknowns that we have RA is one unknown, RB is another unknown, MA is another unknown. In this problem, we are having three unknowns. Okay, so we have to find the value of three unknowns. We have three unknown reactions. We have unknown reaction RA, we have unknown reaction RB, and we have unknown reaction MA, reaction moment. Okay, so we have three unknowns. Let's see how many equations we have. As far as the equations in hand we have, first we'll write the equation of equilibrium. We have RA plus RB minus P equal to 0. That is RA plus RB is equal to P. This is our equation 1. And our second equation is we have MA, and we have the moment because of P, that will be minus PL by 4. That's minus PL by 4. And the moment because of this RB is anti-clockwise. It is RB into L. This is equal to 0. Okay, this is equation 2. So we have two equations of equilibrium. We have equations of equilibrium 1, we have equation of equilibrium 2. In order to find the value of RA, RB, MA, we have three unknowns, but the number of equations that we have in hand are only 3. Okay, so we have two equations in hand. The number of equations that we have in hand are 2. We have two equations. Okay, we have two equations in hand, but the number of unknowns we have 3 number of unknowns. What we will do, the number of unknowns we have are 3, while as the number of equations we have are just 2. In order to solve an equation of 3 unknowns, in order to solve an equation having 3 unknowns, in order to solve this problem having 3 unknowns, we need 3 equations, but here we have just 2 equations. So when the number of unknowns are more than the number of equations available, we say this is a case of statical indeterminacy. This problem of beam is a problem of statically indeterminate case. This is statically indeterminate case. So this case becomes a statically indeterminate case. Okay. So, and the difference is the number of unknowns are 3, the number of equations are 2. 3 minus 2 is 1. We say degree of indeterminacy is 1. We say its degree of indeterminacy is 1. Its degree of indeterminacy is 1. Okay. Okay, we say its degree of indeterminacy is 1. Okay. As is given here, if the free body diagram, as is given here, if the free body diagram, in the free body diagram, there will be 4 unknowns, and there are 3 equilibrium equations. The beam is classified being indeterminate of first degree. Okay, so when in this, as we'll see in the coming examples, sometimes we'll be having 4 number of unknowns and we'll having 3 equations of equilibrium. So we will say that it is having the degree of indeterminacy is 1, as is in case of this cantilever beam, which is supported at the free end. the degree of indeterminacy is 1. It is having degree of indeterminacy equal to 1. Okay. In the same way, we have another types of beams that if, as is given, if the beam remains stable, so the same, in similar manner from here, in similar manner, the continuous beam is indeterminate to second degree, since there are 5 unknown reactions and only 3 available equilibrium equations. Yes, I will tell you what it means. So first I'll conclude from this, that is, as far as this type of beam is concerned, in this type of cantilever beam, the number of reactions that we have, the number of unknowns that we have are 3, while as number of equations that we have is 2. 3 minus 2 is 1. We say this is statical indeterminacy of degree 1. Okay. In the same way, we have another types of statically indeterminate beams, what we call as the continuous beams. Okay. We have to do the analysis of continuous beams as well. Like this beam. This type of beam is called a continuous beam. As far as a continuous beam is concerned, in a continuous beam, as we will see in the coming classes, that a continuous beam is having degree of indeterminacy. It starts its degree of indeterminacy. A continuous beam's indeterminacy, degree of indeterminacy is 2. You should always remember it. Okay. So the simplest way of continuous beam is having degree of indeterminacy equal to 2. We'll see what we mean by the continuous beams in the coming classes. But here we should say that this type of beam is called a continuous beam, and this beam as well as this beam, this is the free body diagram for this continuous beam. These types of beams are, this type of beam is called a continuous beam, and it's one of, and it is one of the statically indeterminate beams. As far as the continuous beam is concerned, it's one of the type of the statically indeterminate beams.